All right, good morning. Welcome to our first meeting of Math 1240, section A02. Hopefully, you're in the right place, but you found your way here, so probably. My name is JD Neer, and if you are wondering what I look like, that means you didn't do your homework for today. So I sent out a link to an introduction video that has my face. I'm sorry you don't all get to look at my face during these classes. I've got this overhead camera. This is how I like to do lecture. Never been one for tablets. This is the closest I've been able to get to a whiteboard. So, seeing a lot of this over the course of the semester, and hopefully at some point we'll all be back in person and we'll get to see each other's bright and smiling faces early in the morning. Okay, so I want to avoid repeating what I said in the introductory video as much as possible, but I do want to start with a couple things, going through the Learn page in a little bit of detail, a little bit about the course structure, and then my expectations for you / how to do well in this course, and then we'll jump into some math. So first, let me share. So this is our Learn page. Here's where you will land when we start. Couple of important things to definitely be aware of. The syllabus page, this was your homework for today, to come in having read carefully the whole syllabus. Not too long, has lots of important information. Going to mention a couple key things here, but I'm not going to go through everything right now. I trust you can all read through it. Second important document on here is our 1240 definitions and theorems. So the syllabus has everything you need to know about the course. This definitions and theorems is everything you need to know in the course. So all the material we talk about is going to be in this one document. Please do not try and read this whole document today. What I do want you to do is, before each class, come down into A02 specific. And if you look at lecture information, you can see what is expected before each class. So today, before class, I've asked you to watch the introduction video, where you can, again, see my face, talk a little bit more about the syllabus, read through the syllabus carefully, and also read through the information specific to our section. And then also, I gave you some parts of our definitions and theorems to read through. This was posted kind of late last night, so if you didn't get to that, that's okay. And also the problems to work on after lecture today. And you can already see I've got this all up for lecture 2 as well. So we'll talk about this more when I talk about how to succeed in the class, but here is our lecture information. Here is that section specific information I mentioned. So this is my name, how you can contact me, office hours, which are really important, good to know about. Again, we'll talk about that more in a second. Couple things I want to mention that did not come up in the introduction video. So this is our A02 specific section. You are completely allowed, if you are so interested, to dip into other sections, see what they got going on there. Question, maybe? Or just unmuted mic?
Không, có nghĩ là một tivi phải cô chủ.
Bật cái máy chiếu lên. Một máy chiếu vậy.
Cô chủ vậy.
Wait, let's mute everyone else. All right, sorry about that. Okay, so you should feel free to dip into other sections. In particular, the other instructors for this course have some videos from previous semesters. So if you're the type of person that likes to watch multiple videos, get different viewpoints on things. Those are available. I don't have videos from previous semesters. I haven't taught this course at the University of Manitoba in previous semesters, so they don't exist, so I don't have them. This is potentially where you'll be able to find the recordings for this lecture. Couple different technical options I have for that, but if they live on Learn, then here's where they will live. Other things I want to point out did not make it into the welcome video. You've got 2 tests / quizzes already set up for you here. The first is the honesty declaration. You should read through this at some point. It should only take you about 5 minutes, if that. Just agree to our terms for being in the course. In the syllabus, it says we won't give you credit for anything until you finish this, so make sure you finish that right away. And there's a practice quiz, just to get you used to how the quizzes work, what they will look like, what to expect for that. Okay, so let me stop sharing. And let's close up that. So a little bit more about the quizzes and the course structure in general. So the way your grade is calculated, and this is all in the syllabus, but I just want to cover it. You have 11 quizzes, of which your top 9 count. So you get to drop your 2 lowest quizzes. Each quiz is 15 minutes, which you get to choose when those 15 minutes are. We give you an 84-hour window. It's across a weekend, so it opens on Friday afternoon and closes Monday at midnight. You get to pick the best 15 minutes for you, sit down, take it during that window. We also have 5 tests, of which your top 4 count. And these tests are going to be 35 minutes, plus an additional 10 minutes to upload. I do strongly suggest stopping your test after 35 minutes, using those full 10 minutes to upload, just in case something goes wrong. You can always go back if you've uploaded successfully, spend another couple minutes working, and then re-upload your answers. But you don't want to run out of time on these tests, because we're really serious about the time limit. We have a 20% penalty per minute late. And we're going to be pretty strict about this. Because we are giving you those full 10 minutes to upload at this point, hopefully you're pretty familiar with how to upload work to a class like this. And then there's going to be a final exam. And at the moment, that final exam will look a lot like a test, slightly more involved, time limits in place there. I don't know. I'm hopeful by the time it comes to the final exam, we'll all be back in person, but we'll see. Cannot see my screen in the webcam view. Interesting. Yes. It's yeah, so you should be able to change the size here. I might be able to I did stop sharing the screen. I am writing things in the webcam view. And I should be able to force everybody to see my screen nice and big. Layout. Sync my stage for everyone. All right, so now that should show my screen nice and large. And welcome, Sammy Wynn. For some reason, WebEx has decided you are my special student this morning. You get highlighted. Just WebEx doing WebEx things. All right, so change the layout. Our test's open book, handled in the syllabus. Good question. There's a list of what you can use in the syllabus, both for in-person tests and online tests, depending on when we take them. But yes, you can use your notes and book, but not any other online resources. Tests will be during the tutorial class, correct. So in addition to this lecture section, you have a different course, different Learn page for your tutorials, different instructor for those. They'll let you know how to connect to their tutorials. They start next week, not this week. And all the tests will happen in those tutorials. Okay, now changing layout can work for all. Great. All right, so everybody can see what I'm writing now, I hope. All the joys of remote learning. I'm a big fan of in-person classes. I taught my class in person last semester. It was a small class. Going back to online learning is not exactly my ideal situation, but keeps everybody safe, so I guess we're on board. Okay, back to about the course. So this is how your grade is determined. I'll be upfront with you. Not listed on here is homework. Right? There's no traditional homework that you do a bunch of problems and then you submit those problems and we grade those problems. That's not part of how your grade is calculated directly. However, there are homework problems for this course. I'm going to say that they're strongly recommended. So the homework problems are back on Learn. So I'll go back to, back to here. Under course documents, we've got these suggested practice problems. So this is a list of problems out of the textbook. And when we say suggested, here's what I mean. You should do all of these problems. You should consider them homework. And if you're coming across a problem and you do it and it's easy, and the next one looks the same, you should feel free to say, all right, I've got an idea of how this is going to go. Maybe I'll skip this one. You should not ever go, I don't need to do the homework for this section. I really understood it. You should at least try some of the problems. But I'm not going to come through and check that you did problem 1 and 3 and 4 and 5 ABD and 6 AB, which is not part of the course. But if you want to do well in this course, doing practice problems is crucial. If the first time you're doing problems is on the quizzes, you're not going to do as well in the quizzes as if you did the homework problems. So that's how those work. All right, back to here. So how do you do well in this course? What are the expectations? What's the goal here? So there's three phases here: before class, during class, and after class. So before class, I've got the expectations on that document that I showed you, the lecture information in our specific section. So check the lecture information document. And read the appropriate sections. This gets you ready for class. There are a lot of definitions and sometimes long lists of important information that if I tried to give them to you in lecture would just fall completely flat. It'd be long and boring. I don't want to teach that way. You don't want to learn that way. So some of this information before lecture, I need you to read through. They're going to be relatively short, 3, 4, maybe 5 pages at a time. This is just to give you an idea of what we're going to talk about going in. All right, a couple of questions. We ask homework questions of the textbook in your office hour. Yep, we'll talk about that more in a second. What is the 84-hour window? For the quizzes, you will have 84 hours during which you can take the quiz, but you only get 15 minutes to take the quiz. So in this 84-hour window, you pick when to open the quiz. Once you open it, a 15-minute timer starts. During those 15 minutes, you take the quiz, but you get to pick which 15 minutes those are. This course is really hard, and studying every day is not a deal breaker. We'll see. See if it's hard. I don't know. Do we have a record? Yes. So, during class. Thank you. Perfect segue. So, these lectures will be recorded. I will make them available to you. My strong advice is to attend live and take notes. And the reason for that is that my lectures are not just going to be me talking for 75 minutes. That's just not how it's going to work. I don't believe in doing lecture that way. In fact, this class might have, this first meeting might have the most of me talking, just because all of this explanation material kind of necessarily is me talking. But a lot of what we're going to do in class is I'm going to give you problems, and then I'm going to shut up. And I'm going to have you think about it, maybe even talk about it with each other in the chat, totally fine. And then we're going to regroup, talk about the answer together. Doing these problems with everyone else in the class, getting real-time feedback, asking questions in chat is a crucial part of learning in this course. So I'm going to make the recordings available so that you can go back and review what we talked about in class. And if you miss a class for some reason, I understand this class is early. I know things happen. I know sometimes, you've got a late night for one reason or another, you miss a class. Hey, recording's available. Really suggest against making it a habit. Really want you to be here. Going to try and make it worth your while. So, yes, recordings will be available. Don't suggest relying on them. After class, last section. After class, go off and do the suggested problems and ask for help. Squeezing it in there. Okay. So, when I say ask for help, what do I mean? Oh, good question. Where can we find the suggested practice problems? So I want to go back. Are here on the Learn page under course documents, fourth link down here, suggested practice problems. Can also get to it if you prefer from the lecture information page. This is where I put it. Yeah, suggested practice problems here as well. So a couple different ways to get there. So when it comes time for help, how to get help. So the answers to the practice problems are not posted. So if you want answers, if you want to check them, 2 good places to do that. First is office hours. So office hours are like optional additional lecture periods. You are not required to show up to office hours. They are drop-in. They're completely optional. All I'm doing during these office hours is answering your questions. Just sitting in a WebEx call, waiting to talk about math with you. So here are my posted office hours. Mondays, 10:30 to 11:30, and Thursdays, 11:30 to 12:30. So every week, starting this Thursday, if the university is in session, I will have a meeting. I'll be open during this meeting. And like I said, not required. Come and ask your questions. If you just want to hear the questions other people are asking, totally fine as well. If these don't work for you, or if you're really concerned, you want a little bit more one-on-one time, I can also schedule office hour appointments with you. Just make your request by email. Let me know when you're available. We'll set up a 15 or 20-minute meeting. We'll do some really intensive one-on-one stuff. Happy to do that if you feel that's necessary, or if you can't make these drop-in office hours. That's one place to get help. The other place is under the communications tab in discussions. So we are going to be using the discussions form pretty heavily in this class. If you email me a question, I'm going to post it in discussions and answer it here. Couple reasons for this listed in the syllabus, but mostly it's because we can get you answers faster this way. There are 3 instructors for this course, 1 for each of the sections. All of us are able to answer your questions regardless of which section you're from. So if you've got a question, post it in discussions, we'll get it to you faster. Also, you might go to post a question maybe about a homework problem or maybe about a definition or something, find out, oh, hey, look, it's already been answered. That gets you the answer even faster. Okay. Look at my list. That's what I got for course stuff. We'll stop the share again. Questions at this juncture? It was a lot. It was like 22 minutes of just talking about the course. What do you want to know about how this course is going to work? While I take a sip of water. How do you go with the labs? Good question. So each of your labs has its own instructor and its own Learn page. Your lab instructor on your lab Learn page will give you instructions on how to connect to lab. Those might not all be set up and running yet, because we don't start labs until next week. Some of the instructors are still setting some things up, but you should be able to find your lab instructor on like Aurora and email them if you're concerned about that. Is there a textbook for the course? There is. So there is a traditional book textbook. The author is Grimaldi. We will do things slightly different than is done in Grimaldi. So we also have the theorems and definitions document. How do you compare the two? The theorems and definitions document has all of the core information that you need, none of the nice words that go with it, right? No practice problems, nothing explaining how things work. It's just like definition, definition, theorem, definition. So not the easiest thing to read casually, really just a good reference to get you prepared for class, where we'll talk about stuff in more detail. There is a library version on reserve, so I don't think you have to purchase the physical book. I think that there's a way to get a digital version. For the suggested problems, is there any answer key? So no, there is no answer key. As far as I'm aware, I don't have an answer key. If there is one, I'd be interested in it. But the idea is that you do a problem and you know you're right because you have solved the problem. We'll talk a little bit more about that in a second. But if you have questions about it, discussions is a great place. Office hours are a great place. Maybe some of them are answered in the back of the book, but yes, the suggested problems are from the textbook. They're from Grimaldi. The practice problems are the best way to prepare for the quizzes. Yes, the quizzes will not come directly from the homework. but they're similar-ish. And then the quizzes will give you a pretty good idea of what to expect on the tests. These are good questions. I like these questions. Other things you want to know. Are the tests cumulative? I'm going to say yes, with a heavy focus on the recent material. So a lot of the ideas in this course build on each other. So we're going to focus, each test will focus on the most recent material, but you might need some of the ideas from previous tests. Okay, so Grimaldi might have some of the answers to the odd numbered problems, but answers are also different than solutions. So maybe some help in the back of the book, but also still good to use resources when you have questions like office hours or discussions. This is all good. I like these discussions. Please feel free. Anytime during lecture you got a question, you want to post it in chat, that's fine. If I'm missing a question, you want to unmute, I got no problem with that. Not real formal on the whole class thing, so yeah, let's work on this together. Okay, I've been talking a lot about a math class and not been doing a lot of math. So this is a math class, let's do a math problem. All right. Let's do a math problem. If we look at the integral from 0 to 6, the integral from x over 3 to 2 of x times the square root of y cubed plus 1 dy dx. Now, looking at an integral like this, dy is our inner integrand, but I don't know how to take the square root of a cubic. Clever idea. Let's rearrange the order of integration. Looking carefully at my bounds of integration, I go x goes from 0 to 6. Y ends at 2 and starts at the line x over 3, which means I'm integrating over this area in the region. So if I solve this equation for x, I get x is equal to 3y. This lets me reverse the order of integration so that my y is going from 0 to 2 and my x is going from 0 to 3y. I'm going along the x direction. My integrand doesn't change, but the order of my differentials changes. Now I can easily integrate x, this stays constant, to get the integral from 0 to 2. This stays constant, and I get a 1/2 x squared evaluated from 0 to 3y. dy, evaluating that's going to give me square root y cubed plus 1, 9/2 y squared dy. This is set up beautifully for a nice u substitution. I can make u equal to y cubed plus 1, which makes my dy equal to 3y squared dy. Substituting that in and, of course, changing the bounds, I get the integral when u goes from 1 to 9, square root of u du, which is simply 2/3 u cubed, times the 3/2 that's left over from this, evaluated from 1 to 9, which will give me 27 minus 1 is 6. All right, beautiful problem. If you didn't follow all of that, that's fine. This is not a calculus class. This is a multi-dimensional calculus problem. Why did I do this problem? Why do I start this problem off this way? Yes, I'm sorry, du, of course. I mean, the du should be 3y squared dy. For most of you, all of the math that you've taken so far is preparing you to do a problem like this. Now, maybe you haven't taken a calculus class yet, so these integrals look a little bit scary. Or maybe you've taken a one-dimensional calculus class, So when I got to this step, you were able to follow, but the beginning was a little bit harder. Or maybe you've taken a multidimensional calculus class and you've seen a whole problem like this. In any case, even if you haven't taken any calculus, at the very end, you know how to plug in 9 to an equation like this. Do 27 minus 1. But all of this is a calculation. And calculations are not what this class is about. This class is not going to have to do with anything in this problem. I mean that all the way up from the multidimensional calculus part of the problem, understanding what this means, understanding this nice region, all the way down to the bare concept of, here's a value, I want you to simplify it and find an answer. Calculus is not mathematics. It's a part of mathematics. It's a beautiful, deep theory, but it's not all math has to offer. So I want to do another problem. Get rid of this. Also, sorry if I scared anyone. Here's another problem I want you to think about. And this time I'm actually going to give you a second to solve it. Suppose we have a chessboard. It's an 8x8 chessboard. 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. And so it's chess or checkers, whichever you prefer. Every other square is black and white. I've done something terrible. Sorry, that square should be white. Failed my checkerboard pattern right away. But I'm going to do one more thing to this board. And I'm going to remove 2 of the corners. So this corner is going to go away. And this corner is going to go away. And this square should be white. But I colored it in incorrectly. All right, you get the idea. 8x8 chessboard or checkerboard, but 2 of the corners are removed. And I want to cover my chessboard with dominoes. They're 1x2 dominoes. They've got 1 black square and 1 white square. So here's my question. Can you take a bunch of these 1x2 dominoes and cover the chessboard with these 2 corners removed? So here, let me start us off. I'll try, make an attempt and see how it goes. So 1 row, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7, 8. Good. And then 1, 2, 3, 4, 5, 6, and 7. Not the prettiest chessboard in the world. And now let me just start placing down dominoes. So maybe I put 1 domino here. I cover those 2 squares. Put another one here, here, and let's try this. Here's how I'm placing all of my dominoes. Nice consistent pattern. And that square is sort of awkwardly left out. And I've got 2 squares left over. So this didn't work out. Right, if I place down these dominoes, I still have these 2 squares that I didn't cover with dominoes. And the way I laid them out, I can't cover them without the dominoes falling off of the board. So I'm going to give you a couple moments now. This is what I mean by I'm going to shut up and let you think. Give it a try. See if you can come up with a way to cover this board with, again, the two corners missing with your dominoes. So one of the suggestions from chat is to use a linear recurrence to maybe count the total number of methods. Sounds like a good computer science idea. I don't even want the number of solutions or like a strategy. I just want to find one way to cover it. I want to cover every square with these dominoes. So give it a try. If you're sitting just waiting for the next part of the lecture, give it a try now. Still going to give you another minute or two. Can we use dominoes that overlap? No, sorry. That's a good question. The goal is to have none of the dominoes overlapping. We want to cover this chessboard with dominoes, so each square has exactly one domino on it. Break up one domino, put it in the two corners. Yeah, well, your grandma's going to be real mad if you break her dominoes. Sun is shining through my window, illuminating the page a little bit. There we go. All right. Logan's winning my favorite student award. Willing to upset his grandma to make his math teacher happy on day one of class. That's dedication. Okay. Let's gather back together. Anyone succeed? Anybody in class find a way? Glue it up later. Find a way without breaking up dominoes, without overlap, to cover the board. I'm gonna guess nobody did. Always seems like there's two squares left over. Seems like it should be impossible. So don't worry. I've set you up with an impossible task. There was no way to make it happen. But here's the point. If I tell you, no, you can't do it, it's not really satisfying. You're just like, well, but I want to, right? It's a problem. I want to solve the problem. What do you mean I can't do it? So let me give you an explanation. If I look at my checkerboard pattern, which I failed miserably in actually coloring in. And I take a close look at my dominoes. Every domino has a black side and a white side, which means every domino, no matter how I place it, is going to cover one black square and one white square. But if I look at this board, when I cut out the two opposing corners, those two corners were both black. So originally, I had an 8x8 board. That's 64 squares, of which I had 32 white squares and 32 black squares. When I cut out the corner, the two opposing corners, those were both black squares. So what's left? I've got 32 white squares, but only 30 black squares. Every domino is going to cover one white and one black square. So when I've covered up all the black squares, I have to have two white squares left over. There is no way to cover the whole domino board because there's always going to be two white squares left over because every domino covers one white and one black square. Okay, so let's bring back this problem for a second. This problem only cares about the answer, which, by the way, is not 6, 26. Hopefully everybody knew that part. The answer is the point of this problem. How you get there doesn't really matter as long as you got to the answer 26. It's because this is a calculation. If you're doing a calculation, what matters is the answer. In this problem, the answer is no. The answer is not interesting. If I just tell you the answer, no, you can't do it, you don't feel satisfied. Satisfaction comes from the explanation. The explanation of why you can't do it. That every domino has to cover a black and a white square, but there are more white squares than black squares. Once you see that explanation, you understand why the answer is no. The fact that the answer itself is no is sort of incidental. The explanation is the part that matters. Now, believe it or not, this is a math problem. This is a question we have about the universe, and we're using math to answer it. It's not a calculation, which is most of what you've seen in math classes so far. What we needed was a logical explanation for why the answer was no. And that is mathematics. Before the explanation, we don't know the answer and we don't know why the answer would be right, but the answer explains everything we need to know about the problem. The explanation explains everything we know about the problem. So what I've been calling an explanation is really a proof. This class is about proving things. It's about answering questions where the explanation is more important than the answer itself. So you've spent a lot of time in a lot of different math classes doing calculations. You've spent a lot less time writing proofs. Maybe you've done a geometry class that had some two-column proofs in it or something like that. You've done a little bit of arguing, but most of what you've been focused on so far is calculation. So this class is at the same time going to be simpler than what you've seen before, and sometimes harder, because you're building up something new. You're focusing on proofs instead of calculations. We're not building on ideas you've been working on since kindergarten. We are trying to build up a new concept of mathematics. Okay, I want to focus on another problem. And remember, our goal is to think about proofs. It's to think about explanations. I'm not worried about the answer. I'm worried about the why. So here's the question. I feel like I don't have to give you as much time to think about this one. So your instinct, because you've been taking math classes that have been focused on calculation for years, is to go, oh, I know the answer. The answer's 2. And that's correct. Not here to tell you that 1 plus 1 is not equal to 2. Definitely the answer is 2. But that's a calculation. I wanted you to think about how you would explain this. Why is 1 plus 1 equal to 2? Now maybe you can stop and think and go, okay, well, if I have 1 apple and another apple, that means I have 2 apples. Which is true. But you can go a little bit deeper. In fact, you can go really deep. So in 1910, 2 mathematicians, Whitehead and Russell, proved that 1 plus 1 equals 2. It took them 379 pages to do so. How could it have possibly taken them 379 pages? Well, it's because they had started from basically nothing. There was no such thing as 1. There was no such thing as plus. There was no such thing as equals. They started from scratch. They started from very, very basic ideas and built them up to define 1, to define plus, to define equals. The answer is not the point. 2 is not the goal of this. They started from really, really basic mathematics and built all the way up. So what is a proof? A proof is a series of logical steps, one leading to the next, that start with basic assumptions and lead to the conclusion. If we think about our chessboard problem, our basic assumptions are that each domino covers 1 white square and 1 black square, and we have 32 white squares and 30 black squares. Our logical step is that if we cover all the black squares, there'll be 2 white squares left over. Our conclusion is you can't cover the whole board. That's a proof that you can't cover the whole board. But here's the thing. Who decides what assumptions are basic? Who decides what steps are logical? We go back to this calculus problem. Maybe some of you are convinced by my answer of 26, but it sounds like a lot of you did not follow what was going on here. If I take this problem and show it to a professional engineer, they'll go, okay, yeah, I checked your work. That makes sense. I agree with you. But if I show it to a 1240 student, they go, I don't know what's going on. I don't know if you're right or wrong. You could have made a mistake somewhere and I wouldn't know. So what counts as a basic assumption, what counts as logical steps, that depends on the reader and the writer. A proof is a discussion. A proof is a writer talking to a reader through time and space. In order join this mathematical community, in order to be able to have that conversation, you need a basis that we can all work from. And this class is about building up that basis. We're going to start with some really basic concepts. We're going to explain why they're basic, why they work. We're going to talk about how logic works. We're going to talk about how sets work. We're going to build up to some slightly more complicated things like graphs. We'll talk about infinite sets and counting, and we'll prove some basic things about numbers. And the idea of this class is not to cover very complex calculations. It's not to do calculus. It's about how to build up this vocabulary to talk about proofs, so that we can explain things to each other and understand and all be on the same page. Okay, so that's my introduction to the class. We still have about 25 minutes left. I'm going to start doing some of section 1. But I also recognize that this is a long class. It's 75 minutes. Especially in a remote class, it's hard to stay focused that whole time. So let's take a 3-minute break. I've got 9:21 right now. We'll come back 9:24-ish. Go get a snack. If you want some breakfast, go check your email. Watch a TikTok video. I don't care. Clear your brain. Take a second to mentally reset. We'll come back in 3 minutes. We'll do some math. Okay, let's reconvene, close down your TikTok video, come back from the kitchen. We're refocused. We've got our energy back. Let's jump into some logic. So I want to start with the definition. A proposition is a declarative statement that is either true or false. So, as an example, I can write down the statement 2 is an integer. Right? That is a statement that is true or false. I could write down it is sunny in Winnipeg this morning. That's a statement. You can go out and verify it. It is in fact sunny. I can even write down pi is an integer. This is a declarative statement. It's not true. It is false, but it's still a statement. If I write something like, do your homework, this is not a statement. It's not declarative. So this is not a proposition. Do your homework doesn't count as a proposition. I could also write down something like x is an integer. X is an integer is declarative, but I can't test if it's true or false. I need to know what x is. If x is 2, then the statement is true. If x is pi, then the statement is false. But it's not one or the other. It depends on the value of x. So this is not true or false unless I know what x is. In logic, propositions are the basic things we work with. So just like in arithmetic, you work with numbers, in logic, we're going to work with propositions. And just like in algebra, you can use variables to stand in for numbers. We can use variables to stand in for propositions. So I can use P and Q, as proposition variables. So what can I do with these variables? I can't add them together. Doesn't make sense to add 2 as an integer plus it is sunny in Winnipeg this morning. But I still have things I can do with them. One example is not P. So this is negation. And we read this symbol as not. So this is not P. And not P is a proposition that has the opposite truth value of P. And we can record what that means in something called a truth table. table. So here's my variable p, and here's my proposition not p. If p is true, then not p is false. And if p is false, then not p is true. Okay, that's how negation works. Another thing I can do, if I have two propositions, I can combine them with something called a conjunction, which is a little caret pointing upwards. This is a conjunction, and we read it as P and Q. And this is true when P and Q are both true. So again, I can make a truth table. This one has two variables, which I separate with a single line, and then my double line for my my proposition, P and Q. And if I have to write out true and false a whole bunch, it's going to be a lot of work. One of the running themes I'm going to talk about a lot in this class that mathematicians are lazy, so frequently we write 1 to mean true and 0 to mean false. So if P is true and Q is true, then P and Q is also true. But if P is true and Q is false, P and Q is false. If P is false and Q is true, P and Q is false. And if P is false and Q is false, then P and Q is also false. So I filled in a truth table for P and Q. I'm going to try and leave this truth table up. So the next one, we've seen conjunction. The next one is disjunction, P, disjunction Q, an arrow pointing down. And this means P or Q. So this one is true if P is Q or if Q is true. So exercise, I want you to right now fill in the truth table for P or Q. Go ahead, take a minute. We can copy over all of our possible inputs here. 1, 1, 1, 0, 0, 1, 0, 0. And now you take a second, fill in that column. Give you maybe a minute to think about it. All right, good. Got some answers in class, in chat. They pretty much seem to agree. So if neither P nor Q is true, then P or Q is false. If P is false but Q is true, well, at least one of them is true, so that's good. If P is true and Q is false, again, at least one of them is true. And then this is the one that trips people up sometimes. If P is true and Q is true, that's still true. One of them is true. Both of them are, but at least one of them is. So this disjunction, we think of it as not exclusively one of them. If I say you can have ice cream or cake, to a mathematician, both is a perfectly acceptable option. To your mom, maybe not so much. But, you know, hey, you can say, well, my math teacher taught me that or is inherently inclusive, so I'm going to have ice cream and cake, and then you'll have a stomach ache, and you can blame me. I'm fine with that. I'll own that. Okay. So true or true is true. Couple more. So there are lots of these logical connections you could talk about. If you take a computer science class, you might learn about exclusive or. Lots of different symbols for exclusive or. The sun is shining through. Not much I can do about that. Maybe I'll put up some blockout blinds. But there it is. Some nice sun in your morning. Okay, couple more ways to combine our propositions. P implies Q. Implication. P implies Q is how we read this. And this logical connective means that P guarantees Q will be true. If P is true, then Q must be true as well. So let's look at a truth table here. So if P is true and Q is true, then that means P implies Q. P was true and I got Q. So indeed, P implies Q. If P is false, if P is true and Q is false, then P did not successfully guarantee Q. So true implies false. That means that this is not true. P did not imply Q. I had P, but I didn't get Q. Now the question is, what if P is false? What should happen in these two cases? And the way I want you to think about implication is as a contract. We sign a contract. If I hold up my end of the contract, you have to hold up your end of the contract. So imagine this is our contract. If you get an A in this class, your parents say to you, I'm not saying this, don't quote me on this. If you get an A in your math class, I'll buy you a car. I think this math class is very important. Child, son or daughter. If you get an A, I'll buy you a car. So what happens? If you get an A and your parents buy you a car, that's true. The implication worked. Your parents were truthful, you did well, you got your car. If you get an A in the class and your parents don't buy you a car, you're really upset. You did what they said, they didn't come through, they broke the contract. That's false. They lied to you. But if you don't get an A in the class, what happens? Your parents said, if you get an A in the class, we'll buy you a car, but you didn't get an A. If you don't get an A and they don't buy you a car, you can't be mad at them. They told you, get an A, we'll buy you a car. You didn't get an A. So this is still true. If you fail to meet your end of the bargain and they don't do the thing, that's fair. P still implies Q. And now, if you don't get an A, but your parents buy you a car anyway, did they lie to you? Now, you're happy because you have a car. But stop and think, were you lied to? You weren't actually lied to, right? They said, if you get an A, we'll get you a car. Turns out they were always going to get you a car because somebody has to take your little sister to dance class and they don't want to do it. So they bought you a car, but haha, joke's on you. She's got dance 5 days a week. She's super into dance. You got to drop her off and pick her up. So if P is false, it does not matter what Q is. If P is false, then P implies Q is true. If you don't hold up your end of the bargain, whatever happens is fine. The only way that P implies Q is false is if you do your end and the other party doesn't fulfill the contract. Now, if that's a little bit unsatisfying to you, I have another logical connective you like more. You might like more. This is called the biconditional. Arrow goes both ways instead of just one way. This is the biconditional. And we read it as P if and only if Q. Again, central theme of the course. Mathematicians are lazy. If and only if is way too long. We'll frequently write this as if with an extra F. So IFF, not a typo. It means if and only if. So let's make a truth table for this one as well. P, Q, P, if and only if Q. So if P and Q are both true, then P if and only if Q holds. If P is true and Q is false, well, P held up its side of the bargain, but Q didn't. So P if and only if Q does not hold. Same way, if P doesn't hold up its end of the bargain, but Q does, then I don't have P if and only if Q. They're not agreeing. But if neither end holds up their end of the bargain, then this is true. This says P and Q happen together. Here they both happen, so it's true. Here neither one happened, so still true. Here only one of them happened, so this doesn't hold. So this is your parents saying, I will buy you a car if you get an A, but only if you get an A. So then they're promising you, look, hey, if you don't get an A, I'm not buying you a car. If you don't get an A and they still buy you a car, they did lie to you this time. Okay. So when we combine propositions like this, we call this a compound proposition. Combining propositions with not, and, or, implies, or if and only if, makes a compound proposition. And a proposition by itself is called primitive. So if I just have a statement like 2 as an integer, or even if I just have the variable p, I call that a primitive proposition. Okay. So one last thing I want to do in class today is I want to look at two different compound statements. One of them is P and Q or R, and the other one is P and Q or R. These are the same symbols, but I've put the parentheses in different places. And here's my question, are they the same? I can check that with a truth table. So I've got P, Q, R, and I want to look at P and Q or R, and P and Q or R. So I've got to figure out all the different possible inputs. If you know how to count in binary, we're counting down in binary. Or any other pattern you like that covers everything. There are 8 different inputs here. And let's just check some of them. I'm running out of time, but let's do this quickly. So if P and Q is true, then I get a 1 here. 1 or 1 is 1. Q or R, well, I have at least one of them. P is true, so I get 1 and 1, gives me a 1 there. P and Q, so I get a 1 there, 1 or 0. True or false gives me true. This is true or false gives me true. True and true gives me true. So they all agree so far. This one's going to be similar. So P and Q is false, right? Because Q is false. But I have false or true. So I still get a true here. This one's going to be true and true. This one, P and Q is false. And Q is false. So I get false here, but I also get false here, so we're good. This one, though, P is false, so P and Q is false. False or true, which means I get a true here. But here, I get false and true. False and true is false. So these two do not agree. That means these things are not the same, which means parentheses do matter. And here's how we showed that they were not the same. We looked at their truth tables. They did not have the same truth tables. So I'm going to stop there. I'm out of time today. But we will come back on Thursday and we'll talk more. Since parentheses matter, we'll talk about how to use parentheses, when to matter, and we'll talk more about this example. Recordings will be available soon. I'm hoping today. I'm figuring out the technology still, so we'll see how that goes. And yeah, other questions, post them in discussions, and I'll see everybody Thursday morning. Thanks for your attention. Have a good one.